Yeah. Thank you. Thank you very much. Okay, I will present. Thank you also for this opportunity. I will present a result that came out after a project that I started here during the Trimester program with Andrea Mondino, and also partially from some nice lectures given by Milman during the same Trimester program. So the project was the one to prove some functional and geometric inequalities for these metric spaces verifying the curvature dimension condition. And we were interested in proving, let me say, a fundamental one of the basic estimate functional inequality or geometric inequalities that you want to prove on a given space. The inequality is the problem is the isoperimetric problem. So it goes as follows. So maybe you already know about it, but anyway, I will say just a few words about it. So you have a space, and where you know how to measure, both volume and perimeter, and the question is, what is the minimal amount of area that you need to enclose the fixed volume V? Another related question that you want to ask is if you have existence of optimal regions, so the one realizing the infimum or the minimum, and also try to understand the shape of the minimizers. And a possible way for a variant of the isoperimetric problem is let me say the isoperimetric inequality stated in terms of comparison geometry. That takes the name of Levy and Gromov, that the one who proved this way, this form of comparison isoperimetric inequality in this setting. So what they proved, they show that if you have a manifold and you have, so here this theorem is just in the smooth word. So if you have a manifold of dimension n and you have a lower bound on the Ricci curvature with positive k, and you take a domain. So here we are assuming E to be a closed bounded set with a smooth boundary. Then the inequality says this Levy-Gromov isoperimetric inequality states that the measure of the perimeter of the set E is larger than the measure of the perimeter of B. What is B? B is a spherical cap. It's a spherical cap where in S. S is the sphere with constant curvature K and dimension, the same dimension of the Riemannian manifold that we are considering. And this inequality has to be also understood when your volume is taken to be 1. So these two fractions here means that you are taking the volume measure on the Riemannian manifold to be renormalized to 1, and the same here on the sphere. So in which way do we choose this spherical cap? The spherical cap is the one that realizes this identity. So will be the one with the same total volume of the set E. So if you take a set E on a manifold with a Ricci curvature bigger than K, then and if you consider a spherical cap in a sphere with the same volume, then the measure of the perimeter of E is larger than the one of that you have on the sphere. This is the well-known Levy-Gromov isoperimetric inequality, and you see here essentially it states that let me say the isoperimetry it's stronger. It's stronger in this space with Ricci greater than K than respect to the one of the sphere. So we want to find a generalization of this result to the framework that we are working in. So for metric spaces. So for metric spaces, verifying the curvature dimension condition. So first of all, let me show you how we can reformulate this inequality in terms of as you see here, we are considering a measure of a smooth boundary. So here we have to be a little bit more careful to use different stuff. So the first very naive way to measure boundaries, it's to use the Minkowski content. That it's a very natural way of measuring the boundary. So if you consider a set E, so this capital E here, a borrowed set. So the way in which we measure the boundary measure of the set E, we just what we do, we take the set E, we do an epsilon enlargement, and then we subtract the measure of the set E, and then we take the limit as epsilon goes to 0. If you want, it's just the blow up of the of the boundary measure of the set E at the first order. So it is maybe easier if I just draw a picture. So if this is your set E, you just do an epsilon neighborhood here. You just take this measure, and then you let the radius of the tubular neighborhood to go to 0. So you make a blow up of this form. So here, clearly here, I mean, this way, this Minkowski constant depends both on the metric that we are picking on the metric space and both on the measures. So as you see, it really reflects both the metric and the measure of the space. Okay. So once that we know how the way we want to measure the perimeter, we consider what is called the isoperimetric profile function. This is just a more convenient way than to state later the isoperimetric inequality. What is this function capital I? The isoperimetric profile function will be just defined this way. So if you give me a volume, I pick the smallest possible boundary measure that I can take fixing this volume. So the classical isoperimetric inequality, in a way, will be what we'll ask for. We'll ask for finding a precise value for this isoperimetric profile function, while the Levy-Gromov isoperimetric inequality simply states that the can be restated in this form. Maybe it's a bit more compact, but it will be useful later for stating our result. We say that if we have a manifold with Ricci bigger than k, then if we consider the metric measure space formed by the manifold, the geodesic distance, and the renormalized volume, then the isoperimetric profile function of this space will be larger than the isoperimetric profile function of the sphere of constant curvature k and renormalized volume measure. So this is just a convenient way to restate the inequality that we want to understand. So natural question now, it's what can we say indeed if we are able to find an analog of this Levy-Gromov isoperimetric inequality, and also if it is true that we have something like this also for negative curvature, because this Levy-Gromov theorem holds for strictly positive curvature. Why we want to before ask this question? Because as usual, we are speaking about comparison geometry. So if you want to have a result for this class here of curvature dimension spaces, in principle, you before need the result in the smooth world to hold, and then you want to understand which type of result you can get on more general space. So there is a very nice generalization of this Levy-Gromov isoperimetric inequality for any case, so also for negative curvature, and it has been done by Emanuel Milman some years ago, I think in 2012, and he managed to get the same type of result of the Levy-Gromov inequality, but also for negative curvature. And actually for negative curvature, the situation is a bit more tricky, because if you do not impose any upper bound and diameter, then the inequality becomes trivial. So you don't have any more strictly positive lower bound on the isoperimetric profile function. So he cleverly thought about to impose this upper bound and diameter, and introduced this condition is called curvature dimension diameter condition. So here there is an additional d compared to the curvature dimension condition. And the capital D here now plays the role of the upper bound and diameter. So if we, a manifold with a window, the manifold with a measure that it's absolutely continuous with respect to the volume measure, so we have it with a density, then this metric measure space verify this curvature dimension condition, condition, if the support of the measure is geodesically convex and diameter at most d, and the generalized Ricci tensor satisfies the usual inequality. Okay, so with this upper bound, with this new condition, Emanuel proved this very nice theorem. So he proved that for any k in R, capital N, capital D, there exists an explicit function that it just depends on these three parameters, such that the isoperimetric profile function of this manifold, that we select verifying the curvature dimension condition, it's bigger than the isoperimetric of this function iknd. and this lower bound it's sharp, in the sense that for a k positive we already know what is the best possible lower bound. We know where are the model space, the sphere, and everything. It's well quite understood. For negative k, actually there is not a single model space, but for each single volume you have a different space, realizing the identity in the inequality on the theorem of Milman. So just to make a small recap, so what proved Milman? He proved that he make a generalization of the standard of the classical Levy-Gromov isoperimetric inequality to any k, to also reach this larger class of parameters. What he did, he also imposed an upper bound. He understood that you have to impose an upper bound, a diameter, and on each of the, as soon as you fix a diameter, there is and for each volume there is a space where this inequality becomes an identity. So this is a sharp inequality, lower bound. So this is the type of inequality that now we want to generalize. And the theorem that we proved with Andrea, now it was like 1 year ago, we proved that the same lower bound holds if we replace the class of manifolds with the class of metric measure spaces, verifying the curvature dimension condition. Obviously, also we also have to impose, in the negative curvature case, an upper bound on the diameter. So the result can be read as follows. So if we have this metric measure space verifying the local curvature dimension condition, anyway, if you don't know what it is, just think about the curvature dimension condition, and the space is essentially non-branching. So again, if you don't know what it is, just think about a non-branching space. So non-branching means that if you have two geodesics starting from the same point, and they meet at some intermediate points, then they have to coincide. So if you have two different geodesics starting from the same point, they can never meet at some intermediate time. So this kind of situation cannot happen. So this means non-branching. So if you have, so the easy statement would be if your metric measure space verify the local curvature dimension condition and it is non-branching, then the same lower bound on the isoperimetric profile function of the metric measure space is verified. And in principle, as an easy corollary, we would recover the Levy-Gromov isoperimetric inequality that was holding when capital N is a natural number and k is strictly bigger than 0. Indeed, and this happens when, if you have a metric measure space verifying RCD star with k and n it's a natural number, immediately we have the space is essentially non-branching. This RCD is stronger than CD lock, and it implies that if you give me any Borel set, then the Minkowski content of this set is larger than the boundary measure of the spherical cap with the same measure of E, renormalized by the total volume of the sphere, where this S is again the sphere of constant curvature k and dimension the capital N dimension. So this is just a restatement of the previous inequality. Why? Because it's just a restatement. Because in the case when we know that the k is strictly positive and capital N is a natural number, this function is explicit, and it's precisely the isoperimetric profile function of the sphere. Because the sphere in positive curvature case is the reference, is the optimal space for this inequality. And okay, so this is the theorem that we proved, and let me just add a small remark to say that this was basically this result was not known before, also for Ricci limit space and for Alexandrov space. So in a sense, this result can be understood to be a new result also in the framework of Alexandrov spaces. Okay, let me now say something about the proof of this result. Actually, the proof goes by what is called this localization method. That it's a method that is very old, and and it's a method that we haven't introduced. So let me just say from where this method comes from. And the basic idea is that if you have an high-dimensional problem, you want to reduce your problem to a lower-dimensional problem. And in particular, you want to reduce an n-dimensional problem to a one-dimensional problem. This sounds very vague, but okay, let me just maybe do an example of this approach. Suppose, for instance, that you want to prove a kind of Poincare inequality. So suppose that you have now we are in Rn. We have a bounded and open set that is convex, and you assume the function to be C1, and we want to prove this estimate. So if we have a function with zero mean, then we can lower bound. We have this type of Poincare inequality. Okay, this is like this theorem goes back to Pei and Weinberg in the 60s, and their proof goes as follows. So their idea is that if you have this this constraint, but you can reduce the set K, capital K, in such a way that this constraint is still true. In a way, you reduce your set K to a smaller subset. So this again sounds a bit strange, but okay, what they did, okay, they said, okay, at first you have to think about that. If you pick one point inside K, you can find an hyperplane going through this point in such a way that still the function f has zero mean inside K with the upper part of the hyperplane, and also on K intersect with the lower part on the hyperplane. So this again, it's better if I make a picture. So here, if we have, if this is K, that is not convex, so K. What we do, we find an hyperplane divided K in two parts. This will be K intersect with H plus and K intersect with H minus. So in these two regions, we can always find an hyperplane in such a way that still this constraint hold on, still f has zero mean. Now suppose that you were able to prove now the estimate that you want to prove on these two smaller regions. So suppose now that you have this inequality on both these two regions. You see that now if you add these two estimates together, they will give you the claim that you were starting from. Why? Because now the diameter of these two smaller regions is just smaller than the diameter above. So if you just sum up these two inequalities, you go back to the one before. So you see that to obtain the first inequality was enough to prove your estimate on both these two smaller regions. But again, you make a reduction to a smaller subset, and still you have the same inequality to prove. Now what they did, they iterated this idea countably many times, and in the end they managed to arrive to a one-dimensional problem. Once that you have a one-dimensional problem, the problem becomes much easier, and once that you have a solution for your one-dimensional problem, you go back to the n-dimensional problem. This was, I think, the first example of how localization method works. And obviously this was in Rn for a different problem than the one that we had. But anyway, this method of localization was then developed by a lot of people, and okay, all of this approach that we saw here for Pei and Weinberger obviously uses a lot the symmetry of the space. Anyway, I mean, there was maybe one of the fundamental contributions in this application of the localization technique to functional inequalities is this paper by Gromov and Milman, Vitaly Milman, where they proved this the isoperimetric inequality for any norm on the sphere using this localization technique without having any use of the symmetrization. So without using any symmetric property of the norm, because they were not having any symmetric property of the norm, they anyway used this localization technique to prove the isoperimetric inequality. So in a way, it was well known to that community that once that you are able to localize the property of your space, and you are able to prove a one-dimensional isoperimetric inequality, then you are able to go back to the full-dimensional isoperimetric inequality. let me say that there was also a crucial application of this localization technique by these three people, Cannon, Lovitz, and Simonovitz, where they proved what is called four-function theorem. This is a general technique to use localization to prove functional inequalities. For instance, log Sobolev, Sobolev inequalities. But okay, I will not have time to speak about this, but you can find, if you Google these three names, there is this four-function theorem that's very nice. Okay, so now where optimal transportation came into play was this paper by 2014, so it was again 2 years ago, by Klartag. It's, he's part of the community of Gromov and Milman, more or less, and his breakthrough was to use L1 optimal transportation to produce a localization of the problem. Now we see in which way. And then the important stuff is that using L1 optimal transportation permits you to use to find a localization of your problem, so a dimensional reduction, also for a general manifold, where you don't have any kind of symmetry of the space. So this is the proof that the theory that he proved goes like that. So start from a Riemannian manifold that is geodesically convex, assuming that it verifies the curvature dimension condition, and take a function that has a zero mean. So we are still with the same constraint that we saw before. Then he proved of the following points. So let's go slowly through these points. So the first stuff that he found was that you can find a partition of your manifold. Each element of the partition is indexed by this index alpha. And the first point is that this decomposition of the space gives you a decomposition of the measure. So the total measure M can be written like as the sum of all these M alpha, summed with respect to some kind of measure Q over the set of indices. Well, I mean, what is so special about this M alpha is that M alpha only see a single element of the partition M capital M alpha. So this is in the second point. So M alpha is just a geodesic, so it's a one-dimensional space, and it contains the subset of this small M alpha. Moreover, so this is just to say that, so these first 2 points is that you have a decomposition of the space, and together with a decomposition of the space, you have a decomposition of the measure. The important stuff, why it's called localization, it's called localization because you localize the curvature of the space on any single line. So for almost every line of this decomposition, the metric measure space that is formed by this geodesic, the restriction of this measure M alpha, and the distance verifies curvature dimension condition. And moreover, the constraint is still verified. So you have a partition of the space where you localize the constraint and the geometry of the space. And the idea of this proof is to take a function f that has zero mean, and the idea is that you can see a function with zero mean like as the positive and the negative part of the function. They will have the same mass, and you want to transport the positive to the negative part of the function. So mu1 will be the positive part of f, and mu2 will be the negative part of f. So mu1 and mu2 will have the same mass, and you want to transport mu1 to mu2. Okay, let me just, okay, this is basically what is called a localization. So you localize the constraint on a one-dimensional space, and you also localize the curvature. Okay, now I want to show you why it's why once that you have this localization, you can prove the isoperimetric inequality. So I'll just skip this slide for a second. You have questions? Maybe? No, they don't have questions. So we want to find a lower bound for the Minkowski content of a given set. So how do? We just go by definition. So you just take the limit of the epsilon enlargement of your set E, and you take a kind of derivative in respect to epsilon. So now what we know is that the measure M has been decomposed in one-dimensional arrays. So from the first line to the second line, we just use the decomposition of the measure that we have found. Maybe I can write it again here. So the whole measure M, it's decomposed as MQ sorry, there's a problem with the indices. Before was m alpha integrated against q d alpha. Here there's a mistake with the indices. So the first line is just to use the definition here of this decomposition that you have found. And again, here you integrate the epsilon enlargement of the set. But now you see that you know that each of these m alpha are considered on a one-dimensional line. So you have to think about that your space has been partitioned in this form. And maybe your set E is something like this. What it's not hard to understand is that if you do the enlargement and first consider this contribution here, this will be bigger than first doing the intersection with each single ray and then doing the enlargement. So and this is okay. Sorry, from here to here it's just thought was anything interesting. From here to here, you see that each of these one-dimensional measures is just concentrated on a one-dimensional array. Now here it's this contribution will be bigger than first doing the intersection. So it's just written here. So if I make an enlargement and then I intersect, this would contains the fact that I first do the intersection and I do the enlargement. So in a way, this means that this ratio is just bigger than the Minkowski content, the one-dimensional Minkowski content. It's just written here. But now we know that we have localized the geometry. So this would be the Minkowski content of a one-dimensional metric measure space, still verifying the same curvature bound. So this will be by the smooth Levy-Gromov-Milman inequality bigger than this capital function I depending on k, n, and d. Evaluated where? Evaluated on the measure of the total set. Okay, now here it looks like that all this procedure works for any one-dimensional localization that we have found, but we still have one parameter freedom of choice. That's the fact that we all these stories start from the fact that you want to localize a constraint. Which constraint you localize? You localize the fact that what you want to localize is the total mass of E. So what it means that a function that you want to localize, you just take f to be the characteristic function of your set E, renormalized minus 1. Clearly, this function will have 0 mean. But now what happens if we know that we have a localization, so this will be 0. But we know that there exists a localization for which on each single ray, still this function has 0 mean. What it means that we just write like that. This will have to be 0. But what it means, remember that m alpha are just probability measures. Everything is a probability measures. But then here, this one just means that m alpha of E divided by m of E, it's again equal 1. So it means that on each single ray, I still have the same mass that I have for the total space. So this means that on each single ray, I have the same mass. So here I had this lower bound evaluated on the total mass of E, but now this is just constant. I can bring it outside, and I end up with a function, with the isoperimetric profile, with this lower bound found by Levy, Gromov, and Milman. So this was just to show that once that you have a localization, you directly have an isoperimetric inequality. And okay, so before, now I go back to the theorem, to the non-smooth localization that we proved. And it's basically the same statement that I showed you before, the one proved by Klartag. So what we prove is that, again, if we have a metric measure space that it verifies the local curvature dimension condition and is non-branching, if you start from a function with 0 mean, with some, let's say that with some assumption on the growth of f, then what I can do, I can decompose my whole space X as a two-part, the Z capital union with T, where we know that over Z, we know that the function is almost everywhere 0, and this capital T will be a kind of transport set, let me say, and this capital T will be partitioned in this family of one-dimensional spaces. So there exists this partition denoted with the xq, with each of these xq is a geodesic, and again we have this localization of the measure, so it's called a disintegration. So the measure M can be reconstructed summing over all this small contribution MQ, and each of these MQ is just concentrated on each of these rays. Still, we know that on almost every ray the constraint is preserved, and along almost every ray also the curvature is preserved. What it means that the metric measure space from the xq, mq, and with the distance verifies the curvature dimension condition. This actually can be made a little bit more explicit by saying that mq, it will be a measure concentrated on a one-dimensional space. So we can say that we'll have a density with respect to the Lebesgue measure, and this density verifies in the weak sense the curvature dimension inequality. So as we've already seen, once that you have this theorem, you directly have the sharp isoperimetric inequality in this way. Okay, I think I will not have time to say why this localization works in the no-smooth world. Let me just say that, again, the idea is the one of transporting the positive part of your constraint to the negative part of your constraint function f, using L1 optimal transportation. If you use L1 optimal transportation, if there are some experts on all L1 optimal transportation, you know that it already directly gives you a partition of the space, because it just gives you all of, what they are called the strain or the transport rays, so it gives you a decomposition of the space. Once that you have a decomposition of the space, there are very general theorems saying that you can associate with the decomposition of the space at the composition of the measure. One of these theorems is called disintegration theorem. So the hard part is to localize the geometry of the space. So to prove that on each of these strain, you're seen as a metric measure space, it verifies the curvature dimension condition. And the point is that this will be, you are in a metric space, and this will be an L1 optimal transportation problem, while all the curvature information are stated in terms of L2 optimal transportation. So you have to play a little bit around with a monotone set and insert inside an L1 optimal transportation some small portion of L2 optimal transportation and use them to prove the curvature inequality. But I think I will not spend too much time on this. Okay. So what I show until now is that if the theorem that we prove is that the isoperimetric profile function of this metric measure space under a curvature dimension condition are larger than this function. They have the same lower bound that was enjoyed by smooth manifold. There is a property of this inequality that is called the rigidity, and says this were known to hold in the smooth world, and goes as follows. If you have a Riemannian manifold with a Ricci curvature larger than n-1, and if you know that there exists a single volume for which the isoperimetric profile function of this manifold coincide with the isoperimetric profile function of the sphere, then you can prove that M, so your manifold is isometric to the sphere. So this is a rigidity theorem that is true in the framework of Riemannian manifold. And the question was, we tried to understand was if the same statement holds also for non-smooth spaces. And the answer to this question is no, because you can find examples of non-smooth spaces having the same isoperimetric behavior of the sphere. And a typical example is the one of spherical suspension. So you take a non-smooth space as a quotient space of this spherical suspension, and if you make the computation, you see that spherical suspension have the same behavior of the sphere. But the next question was if can you prove that these are the only cases where this identity holds? And actually the answer was yes. So we proved this rigidity theorem. So now this is in the framework of Riemannian curvature dimension condition spaces. So if we have a metric measured space verifying the RCD star condition with n-1 and n. And if there exists a single volume for which the isoperimetric profile function of the space coincides with the isoperimetric profile function of the sphere, then XDM can be written as a spherical suspension, as a metric measured space. And the quotient space verifies RCD star, so there is a star, n-2, n-1. So these are rigidity, but also remember that at first we want to understand what is to find precisely an estimate on the minimal amount of area that we needed to enclose a given region of volume V. So now the question is, can you tell me how much is this amount of area that we need? And okay, you can prove actually that if you have equality for just one single volume, then you have equality for any volume. So the two isoperimetric profile functions coincide. And you know the existence of a minimizer. And you know the existence of a minimizer also because you know how this minimizer looks like. But maybe it's more interesting to make a picture than just look at the expression I wrote on the blackboard. But this maybe just says that if you have, let me just draw like this spherical suspension. What it says here is that the isoperimetric regions will be just this part here. So this kind of non-smooth spherical caps. So you see here, or maybe this other region, depends on which part is more convenient for the measures. So just the spherical cap around the two cusps of the spherical suspension. So if you give me, again, let me try to go here. So so the optimal regions are all of the regions that can be written like this. So they will be all the points of the form Ty for which T is just lower between 0 and RV, or T belongs to pi minus RV pi in such a way that they feel the constraint of having the volume that you assign to me. So these are all the isoperimetric region that you can have on a spherical suspension. And okay, also I will be very quickly on why this theorem holds. This theorem holds because we apply the rigidity theorem proved by Ketterer, that is the maximal diameter that holds on RCD spaces. That goes as follows. Once that you know that if you start from an RCD space verifying with n-1 and n, if this space has diameter pi, then you know that this space is a spherical suspension. Once that you know that your space is a spherical suspension, you can do all the calculations and understand which are the isoperimetric regions. So the claim was to prove that the diameter has to be pi. And this again can be obtained by the fact that the isoperimetric profile function behaves nicely under the change of the diameter. So as soon as you assume by contradiction that the diameter is not really pi, so if you assume that the diameter is a little bit below pi, you can easily reach a contradiction with the fact that you have one volume for which you have identity on the isoperimetric profile function. So you have to be a little bit around, but it's anything deep. So then the final question is, okay, now we have proved that we have also the rigidity, the rigid version of the isoperimetric profile, of the Levy-Gromov isoperimetric inequality. So now we know that if you have an RCD space and for a given volume has the same isoperimetric profile function of the one of the sphere with a coordinate k and n, then the space is a spherical suspension. Then the natural question is, what happens if we do not assume an identity, but we just assume the space the isoperimetric profile function to be close? So if we know that this function here, so the isoperimetry of our space is close to the isoperimetry of the sphere, can we say that our metric space is close to a spherical suspension? Because we know that they are the only rigid places. And again, the answer is yes. And again, it goes. It's a kind of a continuity argument. Here, maybe it's written like with the epsilon and delta, but it's always the same. The argument says that for any epsilon, you have a delta for which, if the isoperimetric profile functions are delta close, then the two spaces are epsilon close in the sense of metric Gromov Hausdorff. Two spaces, I mean that there exists a spherical suspension to where my space from where I was starting is epsilon close to that in this sense. Okay, and so actually this is not completely satisfactory, obviously, because it's not explicit. Okay, here it's just a continuity argument. It says that for every epsilon there exists a delta for which we have this statement. While maybe a nice next step would be to find an explicit way of measuring this distance in terms precisely of the differences of the isoperimetric profile functions. And let me say that this theorem anyway has a nice implication, because before there was not a result like this on the manifolds, and so also because on manifold we didn't have now we completely have understood the isoperimetric rigidity. So now what we can say, we know that if you apply this theorem to a manifold, so suppose that you have a manifold with a Ricci bounded below by n-1 minus something more, and assume that you are the isoperimetric profile function of the manifold is close to the one of the sphere. Then what you can do, you can deduce that your manifold, it's in Gromov-Hausdorff close to a spherical suspension. And this was obviously not known before, because if you do not know the rigidity for the closure of your set, you cannot say anything about the being close to a limited model space. So this is a kind of a continuity argument. And okay, this is all I want to say. Thank you for the attention. No, this is really the difference with respect to the smooth. Why on the smooth case this result was not known, only using smooth techniques. No, why? Or maybe you can just smoothen a little bit the spherical suspension and being still smooth, and you will be close to a spherical suspension, not to a sphere. I don't know. It was just I don't know. My feeling would be like that, but. Maybe over an RCD space that in principle can be non-smooth. So I don't know. Maybe it's very strong. I don't know. I don't have a feeling on that, but it's an interesting question. In infinite dimension? No, on the rigidity. At the moment, also the isoperimetric inequality that we proved is just for finite m. But actually, I don't think there is any rigidity. Oh no, he's the expert on rigidity, so. I don't know if there is a rigidity. There is? Okay, yes. No, that's true. But I think our rigidity theorem is really based on this maximal diameter theorem and on the fact that on the localization method. So I would be curious to know if without localization you can obtain rigidity. This maybe should be a first step. Sorry. Sorry? You mean in which? In CD, I think if you take a sphere, I mean, for almost every radius, it should be finite. No, the boundary measure of a sphere, it's if you fix one point and you let the radius vary, for almost every radius it has finite Minkowski content, because it's no. So this is just the same. You asked if there is a non-trivial in a metric space. If you have a set with a non-trivial boundary measure, correct? Yeah. Okay. Yeah. Yeah. Mm-hmm.
The situation becomes a negative case. So you say something about the negative.
Well, actually, this is just for. Yeah, and I think all this technique works for probability. I mean, maybe yeah. I fear also the lower bound on the isoperimetric profile functions is just for finite measures. I'm not sure what happens with random measures. Maybe the theorem is true, but I think there is not an explicit lower bound already present in the literature. D, but this is the AKND just for probability measures. Maybe if you